Is time travel really possible? Well, yes, but only into the future. Let's find out how as we look at the strange case of time dilation. We've already seen what Einstein said in his special theory of relativity. We're now going to use the features of special relativity to see what happens to time for two inertial observers. Let's say we have two observers, Alice and Ben, and Alice is moving at constant velocity and Ben is at rest. What we need to work out is a universal expression for how time passes for Alice and Ben in each of their frames of references. That is, how do each of them experience the passage of time? To measure time, we need some kind of a clock, and in principle, it does not matter what type of clock we choose. It can be anything: a stopwatch, a wristwatch, a pendulum, an egg timer, even the clicking of fingers. They should all be okay in principle as long as they can count out the passage of time regularly and accurately. But the analysis of any kind of real-world clock that we can think of is not at all straightforward, especially in terms of how the clocks behave when moving up to speeds close to the speed of light. The problem is that we cannot just work out how any of the features or mechanisms of any real-world clocks will work when they're moving. And that makes it impossible to be sure that we can compare Alice and Ben's clocks properly in all cases. What we're trying to work out is how time passes in all scenarios, no matter how Alice and Ben are moving or where they happen to be. On Earth, in space, at rest, or moving close to the speed of light. So what we need to do is find a clock that we can trust in all situations. Well, there is one thing we can use that we can all agree on and which is always constant, and that is the speed of light. So let us construct a clock based on light. A light clock is not real. It is just a thought experiment, but it's ideal because it is very simple in its operation. It uses a photon of light to count out the passage of time. And all observers can agree how a light clock works because the speed of light is constant in all cases for all observers. So nobody has any doubt about how the photon of light is counting out the passage of time. It's not known for sure if Einstein used this thought experiment or not, but it has become the standard way of talking about how clocks behave, and so we will use this approach as well. So let's build our light clock. A light clock is made up of two mirrors which are perfectly parallel to each other and a distance L apart. There is a photon of light which bounces back and forth continuously between the two mirrors. Obviously, the photon moves at the speed of light, and everyone can agree on its speed. The passage of time, the tick-tock of the clock, is marked out by the photon bouncing off the mirrors, moving straight up and down. So every time the light hits the bottom mirror, we can say tick, and every time it hits the top mirror, we can say tock. This tick-tock, tick-tock counts out the passage of time in the light clock. Now, let's say Alice is standing on a trolley and the light clock is fixed to the trolley next to Alice. Alice can see the light bouncing straight up and down, so she can count the time passing for her when she looks at the clock. And we know that both Alice and the clock are moving at a constant velocity, which we will call v. Ben is at rest looking at Alice's clock, and he can also count the passage of time by looking at the light bouncing off the mirrors on Alice's clock. Tick, tock, tick, tock. Now, we know that Alice is moving at constant velocity past a static Ben, but from the postulates of special relativity, Alice can claim to be at rest with respect to Ben. So in Alice's inertial frame of reference, she is at rest and it is Ben who is moving past her at constant velocity. Both Alice and the clock are at rest in the same frame of reference. That is, there is no relative motion between Alice and the clock. So Alice is seeing the passage of time on her clock, which is static in her frame of reference. And so Alice sees the light just bouncing straight up and down in the clock. Let's say the amount of time which passes between a tick and a tock, according to Alice, is called TA. This is the passage of time for Alice. Now let's look at things from Ben's perspective. Ben is at rest in his frame of reference, and to Ben it is Alice who is moving past him at constant velocity v. So Ben is watching the photon of light going up and down in Alice's clock, and the amount of time which passes between a tick and a tock, which Ben measures, is called TB. This is the passage of time that Ben measures for Alice's clock. Now, what does Ben actually see? Well, for Ben, Alice is moving to the right at constant velocity v. So as Ben watches Alice's clock, what he sees is that the photon leaves the bottom mirror and starts to travel to the top mirror. But while the photon is moving up at the speed of light, Alice is moving to the right with velocity v. So actually what Ben sees is that the photon moves in a diagonal line to the right because the photon is moving up while Alice is moving to the right. So in the case of Alice, what she sees is the photon bouncing straight up and down. And in Ben's case, what he sees is that the photon moving in a diagonal line straight from the bottom tick to the top. For Alice, the distance the photon travels between a tick and a tock is the separation of the mirrors, which we have called L. Now we know that the speed of anything is distance divided by time, so rearranging this gives us an expression for time. Hence, for Alice, in her static frame of reference, the time which passes between a tick and a tock is the distance travelled divided by the speed of light. So TA equals L divided by C. Ben sees the light go from the bottom mirror, the tick, to the top mirror, the tock. But due to the movement of Alice and the clock, the photon of light appears to move diagonally. Let's call the distance that Ben sees the light travel diagonally as being L dash. Now the horizontal distance between the tick and the tock is given by the horizontal speed multiplied by the time taken. The horizontal speed is the velocity of the train, and we have said that the time between the tick and the tock for Ben is TB. So the horizontal distance can be written as V times TB. And we already know that the distance between the mirrors vertically is L. So we have this triangle as seen from Ben's perspective. We are going to use Pythagoras' theorem on this triangle, and using Pythagoras we can write this expression for the triangle as seen by Ben. We note that the photon travels a distance L dash diagonally from the bottom mirror to the top mirror. The photon is travelling at the speed of light, obviously, and it takes a time TB for this movement from tick to tock. So we can write L dash as being equal to C times TB. We can then replace this expression for L dash into our equation, and we get this. We know from what Alice worked out from her view of the clock that L equals TA times C. So we can also replace this expression for L into our equation for Ben's triangle, and we get this expression. We then can rearrange this expression on the right to get an equation for CTA squared. We have to work a little bit on rearranging this equation, and I will show this but not go through it line by line. Suffice to say, we can then end up with an expression for TA squared like this at the bottom. And we can then take the square root of this expression to get an equation for TA. Now, what we are trying to work out is how does Ben see the passage of time on Alice's moving clock? So to get the passage of time for Ben, TB, we rearrange our expression for TA. And we get this, which is what tells us how Ben sees time passing on Alice's moving clock. Just to be clear, what TB is measuring is how much time passes between a tick and a tock on Alice's clock. The longer the time between a tick and a tock that Ben measures, the slower Alice's clock is moving, according to Ben. Imagine it takes 1,000,000 years between a tick and a tock. So Ben will measure that Alice's clock is ticking very, very slowly. Alice always measures a regular fixed time between a tick and a tock, no matter how fast she is moving, because for Alice, she is at rest as far as she is concerned. But for Ben, the time between a tick and a tock changes depending on how fast Alice is moving. This is quite a subtle point, but it is the central idea of how two observers measure time. Now, if we look at this expression for TB, we can see that when V is 0, that is when Alice is not moving, TB equals TA. This makes sense. If Alice is at rest, then both she and Ben are looking at the same clock and all are at rest. So the time between the tick and the tock must be the same for both Alice and Ben. And so time passes at the same rate for both Alice and Ben. If Alice is moving at the speed of light, which is of course not possible, but we are doing this as a thought experiment, then TB equals infinity. That means that the time between a tick and a tock is infinitely long. That is, it never happens. So time stops on Alice's clock as seen by Ben. All this gives us the parameters that we want. If both Alice and Ben are at rest, then they agree on how time passes. But as soon as Alice starts to move, then Ben measures Alice's clock as ticking more slowly. And the closer that Alice gets to the speed of light, the slower Alice's clock ticks, as seen by Ben. So Ben can say that moving clocks tick slower. That is, time slows down for moving bodies as seen by an external inertial observer. This is what is known as time dilation, and it is an important and very surprising consequence of special relativity. The factor by which time slows down is called the Lorentz factor, after the Dutch physicist Hendrik Lorentz. This factor is usually denoted by the Greek letter gamma, and it cannot be less than 1. Using gamma, we can write the time measured by Ben, TB, as being equal to gamma times TA. So it is a fact which comes from special relativity that moving clocks run slower. So why don't we notice this effect in our daily lives? Well, that is because we live in a world where the speeds are so small as compared with the speed of light that the differences are so immeasurably tiny as to make them invisible to us. The fastest that humans move is when they are orbiting the Earth in space. So let's take the example of the ISS and see what that means if Alice is an astronaut on the International Space Station. We worked out in a previous video on orbital motion that the International Space Station orbits with a speed of about 7.7 kilometers a second. So we can say that Alice on the ISS is moving at 7.7 kilometers a second. And let's say Ben is at rest on Earth and see how time passes for both of them. Now, there is a small problem with this setup, and that is that, strictly speaking, Alice and Ben are not inertial observers. Alice is in orbit, and we know that circular motion involves a continual acceleration towards the center. So Alice is not moving in a straight line at constant velocity. And we could also object to Ben being at rest because the Earth is rotating on its axis and moving through space around the Sun. So technically, Ben is also not an inertial observer. But if we take a small bit of time and a small part of the ISS orbit, we can then regard Alice and Ben as being close enough to being inertial observers, at least for this example, where all we are trying to show is how small the effects of time dilation are for everyday human objects moving. So assuming that we can proceed like this, Alice moving at 7.7 kilometers a second, allows us to calculate the factor by which the time passes more quickly for Ben. If we assume Alice spends a year in space, then we can calculate how much time passes for Ben, and this gives us the news that Ben will only be 10 milliseconds, that is 10 thousandths of a second, older than Alice after 1 year, even though Alice is moving so quickly. This is why on Earth we never experience time dilation in our ordinary lives, because anything we do on Earth is so much slower than anything we can think of in terms of relativistic time dilation. The existence of time dilation is real, and it is common to illustrate it using what is called the twin paradox. The popular telling of this story involves a twin going off on a rocket travelling at close to the speed of light, while the other twin remains on Earth. When the travelling twin returns to Earth, they find that the one who stayed behind has aged by many years, so they no longer look the same. Now, obviously, time dilation does not work just on twins. It can be any two people, and the point is that they will age differently. But I suppose in popular culture, it's easier to picture twins because that is a shorthand for saying they start off with the same age. But we will stick with Alice and Ben and see what happens when Alice goes off in a rocket. Let's assume both Alice and Ben are 20 years old and Alice goes off into space moving at 50% of the speed of light. We can use our expression for TB and work out the factor by which Ben measures the passage of time for Alice. If Alice spends 1 year on her journey, then when she returns, according to Ben, he will be just over 56 days older than Alice. So he's aged a bit, but nothing really noticeable. But what if Alice did the trip and travelled at 99.99% of the speed of light? In that case, when Alice returns, Ben will have aged by nearly 70 years. So they will look quite different. And everything on Earth will have aged by 70 years too. So Alice may not even recognise the new Earth. Imagine how the world changed between 1900 and 1970. A person from Victorian times would not know what to do in the world of the 1970s, with cars, TVs, phones, aeroplanes. It would be all unbelievable. So by travelling at close to the speed of light, Alice has come back to a future Earth. She has seen time pass normally for her while she is travelling, but on Earth, time has passed more quickly. So the Earth has raced into the future in relation to Alice. Hence, it is true to say that all of us, when we move, age more slowly than anyone who stays at rest. It's just that in our world, this effect cannot be measured and has no practical bearing on our daily lives. It is only when people move close to the speed of light that the effects of time dilation will become noticeable. For fans of Christopher Nolan, his film Interstellar had time dilation effects as a central part of the story, even though in the film the slowing down of time for the lead characters happens due to them being close to a black hole and not just because they are travelling close to the speed of light. This time dilation due to gravity is also true, so the film is correct. It's just that we have not dealt with black holes yet. We will do so once we're dealing with general relativity. In the twin paradox tale, it doesn't have to be twins to make the time dilation work, so the twin part is not necessary. But you may already be thinking about the paradox part because there appears to be a problem with all this. We remember that from the postulates of special relativity, an inertial observer can always rightfully claim to be at rest. So the question is this: what if Alice claimed to be the one at rest and said that Ben did all the travelling. In that case, Alice will have aged more than Ben when Ben came back. But this makes no sense. Surely only one of them can actually be the older one. It can't be that both have aged more than the other. Well, the simple answer is that in reality, it is Ben who always actually ages more than Alice. But the full reason why this is so is not at all simple. And to get to the full explanation, we have to go into coordinate systems in space-time and look in detail at frames of reference. That is not possible here, so let me give a hint of an answer, but this is not the full explanation. The reason that Alice cannot claim to be at rest and so age more than Ben is because she is not an inertial observer at all times in her journey. Alice breaks the premise of being an inertial observer by how she has to travel. This is because Alice has some parts of her journey where she has to accelerate. We know this must happen because Alice has to go away from Earth and then somehow make it back. No matter if she stops, turns 180 degrees and comes straight back, or does a very gentle loop back to Earth, in all cases she must change direction at some stage in her journey. And a change of direction is a change in velocity, and a change in velocity is an acceleration. So Alice cannot avoid accelerating at some stage, and it is during this acceleration phase that her clocks stop behaving in a way that is inertial. And the symmetry, for want of a better word, of special relativity is broken. It is because Alice is accelerating that Ben actually, unambiguously, becomes the person who will actually claim to be the one who ages more than Alice. So when Alice returns to Earth, she cannot claim to have been the one at rest because she has not been an inertial observer at all times. And this is why we can say that it is actually Ben who stayed on Earth has become older than Alice. The acceleration is not the sole cause of Ben being the older person on Alice's return, because we can set up different scenarios without acceleration and still see time dilation in action. For example, we could have Alice moving continually past Ben rather than starting and stopping. But all those ways of doing things are more complicated to set up, and it is not helpful to deal with them here. So we have stated the twin paradox in the way it is normally presented, but suffice to say there is a lot more to it in the background, but we're not going to go into it just yet. The idea of time dilation is what is crucial, and it is real, even if the twin paradox presents it in a somewhat simplistic way. We've been saying throughout our dealings with Einstein's theories that there is no absolute time, as there was in Newton's theories. What we have just seen with time dilation is the proof of this. We have worked out how one person can measure how time passes differently for them in relation to time passing for another person. So time really is personal to each of us, and it depends on how we are moving. And there we have it. Moving clocks appear to run slower to someone outside, and this allows time travel into the future. In fact, we are all time travelers when we move. It's just that the time changes are too small for us to notice in our everyday lives. Relativity theory is full of ideas which seem really strange to us because they don't align with our everyday experiences. But that is really because we're not moving fast enough or near enough to strong gravity for them to become obvious. We will look at another strange concept in the next video when we see how distances and lengths can change when we move. But until then, keep thinking physics.